lecture. So Or Patashnik is the PhD student at the Tel Aviv University and also working at the SNAP Research as the intern there as well. And she has done lots of the work, very great work about like image generation and the editing based on the diffusion models. So we have discussed some kind of the basics about diffusion models so far in this class. And she's gonna talk about some kind of the more like some important applications in terms of like how we can utilize some pre-trained diffusion models for many some the diversity applications for the especially for like image generation and the manipulations. So yeah, she'll talk about this topic. So yeah, well, please take it away.
Okay. Thank you for inviting me, Minuk, and thank you for the introduction. And I think we have quite a lot of time. So although we have a Q&A session at the end of the talk, please feel free to stop me if anything is not clear. Okay. So like most of you probably know, in the recent years, we had a huge advancement in generative models and the quality of the images that they can generate and their diversity. And actually, even though that this course is about diffusion models, I think that a huge progress has also been made in other types of generative models, such as GANs and the autoregressive models. And besides the scale and the large amount of data that was used to train these models, something that is common to all of these great models that we see recently is the use of attention layers. So this talk is going to in this talk, I'm mostly going to talk about attention layers. So I guess that most of you at some point saw this figure of a transformer and are familiar with this equation of attention. And to be honest, I actually started to understand what's going on in attention only when I actually play with it. I see that there is a question, so you want to ask something, Sangmin? Oh, okay. So again, you can stop me if you have any questions. So I really hope that by the end of this talk, you're going to have much more insights about attention layers and the application that they enable in generative models. So I'm going to focus on stable diffusion. I guess that most of you are familiar with this. So just to remind you where does attention is used in stable diffusion. So each of the blocks in stable diffusion consists of a convolution layer, followed by self-attention layer, followed by a cross-attention layer. So we have quite a lot of attention layers in stable diffusion. Okay, so now let's actually begin. So let me start by explaining what is self-attention. So the input for this layer is the feature map, which is actually the features of the generated image. And first of all, in attention layers, we project these features into three components called queries, keys, and values. And each of these components has its own role, and we're going to see it soon during the talk. And after we have another thing to mention that again we're going to see it along the talk is that the information encoded in these features is very semantic information. It's not only about appearance and stuff like that, but it's a lot about the semantics of the image being generated. So after we have these three components, the queries, keys, and values, in attention layer, we multiply the queries with the keys. So it means that each of the queries is multiplied with each of the keys, which gives us an attention map per query. Now note that this multiplication is actually an inner product that measures similarity, as always with the inner product. So it actually means that for each query, we have in its attention map, we have the keys that have the most similar semantic meaning to it. Okay, so for example, you can see here two attention maps corresponding to two different queries. So for example, in this map, the query is somewhere on the leg of the bear. So we see that the keys that are most similar to this query are the keys on the legs of the bear. Okay, so these are the attention maps, and after we have them, we multiply these attention maps with the values. So it means that in the output feature map of the attention layer, each feature in each pixel, we have a weighted sum of the values, where the weights for this weighted sum are determined by the attention map, okay, corresponding to this specific location. So a nice example that shows the power of a attention layer specifically for generating image, I think, is this example. So here we see a moon above a lake, and we see that the moon is reflected in the lake. And if we look on the attention map of a point of this red point on the reflection of the moon, so we get something like that. This is, of course, in a specific layer, in a specific time step. So by this, you can see how these attention layers allow the model to model long-range relations. If we've used only convolution layers, it would be very difficult to have accurate reflection of the moon. We would have to have a very large perceptive field, but these attention layers allow us to model these long-range relations. And if we think about it a bit more, why is this the attention map that we get for this point? So as I mentioned before, attention maps basically gives us the most semantically similar points for this specific red point. So what are the most semantically similar points in the image? The points on the reflection and the points of the moon. Okay. So now let's move to cross attention. So this is very similar to self-attention, but here we have two inputs, not only the features of the generated image, but also the input text embedding. So in cross attention, again, we project the inputs into queries, keys, and values. This time, the features of the generated image are projected to be the queries, and the text embedding is projected to be the keys and the values. And again, we multiply each of the queries with each of the values. So for each point here, for each query, we have an attention vector that tells us what are the most semantically similar words for this specific query. Okay, so for example, so this is here, the prompt is a kitten and a puppy. You can see that here there is, maybe, I hope you can see, this is a kitten, this is a puppy. So for a point on the kitten, we're going to have a lot of attention for the word kitten because this is the most semantically similar key for this query. And then again, we multiply these attention maps with the values. And again, for each feature in the output feature map is a weighted sum of the values. Here, the values are coming from the text embedding. And again, the weights for this weighted sum are coming from these attention vectors. And actually, there is another way to look on these cross attention layers, which is typically used. So instead of looking on the attention vector for each query, we can also look on the attention map for each key. Okay, so if, for example, we take the word bear, we can find the queries that are most similar to it. Okay, so we're kind of transposing the attention map. So we can find for each word the pixels that are most affected by this word. And this is also a very useful way to look on these attention maps. Okay, so now I hope that you have some sense about what is the attention and how do we, what is basically what is definition. And now I'm going to start to try at least to convince you that these layers hold a lot of semantic information which can be used for many types of generative applications. So I will start with semantic correspondences and appearance transfer. For each of the topics that I'm going to talk about, I will focus on one or two works, but I also provided here a list of some works that are relevant. Okay, so again, let's go back to the self-attention mechanism. And this is, so previously I said that we're multiplying the queries with the keys. This is the more accurate equation for calculating attention maps. We're not only multiplying the queries with the keys, we're also taking softmax. So let's say I've previously shown the self-attention map of this moon, but let's also look now on the self-attention maps of this giraffe. And specifically, let's look on the self-attention maps for 3 points, the red, green, and the yellow points on the giraffe. So if we look, and again, we're looking on, this is a generated image, and we're looking on the attention maps during the generation of this image. Okay, so if we take this red point on the head of the giraffe, then maybe not very surprisingly, we get most of the attention for the head of the giraffe. Again, why is that? Because these are the pixels that are most semantically similar to this red point on the head of the giraffe. And if we take this yellow point on this leg, so I think this now it starts to get more interesting. We see that we not only get attention for the same leg, but we get attention to all of the legs of the giraffe. So this really shows that actually one time when I gave this talk, and before I showed before I showed the yellow point, someone told me, okay, it's just based on the location. It's based on the positional embedding. But I think that this example shows that the similarity is based not only the location of the pixel in the image, not only on the positional embedding, but actually on the semantics of the image being generated. And again, we can look on the green point, and not very surprisingly, we get attention to the body of the giraffe. And we can take the same points and also look for this example of the zebra. So this time, the yellow point, for example, falls on the grass. So we get attention to the grass. Okay, and now things will begin to be more interesting. What's going to happen if instead of computing this self-attention map by multiplying the queries and the keys coming from the same image, now we're going to do the following experiment. We're going to take the queries from the image of the giraffe and the keys from the image of the zebra. So instead of calculating self-attention maps, we're going to calculate something we call cross-image attention maps. So again, let's look on these 3 points. So if we take this red point on the head of the giraffe, now we're going to get attention to the head of the zebra. And note that the head of the giraffe and the head of the zebra are not in the same location. But again, the reason that we get attention to the head of the zebra is that the keys that are most similar to this query on the head of the giraffe are the keys on the head of the zebra. And this is not a coincidence. Also, if we take this yellow point, a query on the leg of the giraffe, we get attention to the legs of the zebra. Okay, and again, this shows that this semantic information is not only relevant within a single image, but it's also shared across different images. Okay, so for different images, the attention features that we get have semantic meaning that is relevant across images. Okay, so leg is always encoded in a similar way. And for this green point on the body of the giraffe, we get attention to the body of the zebra. So after we did this experiment, and so I think this is quite amazing. Something. So we asked ourselves, what can we do with that? And then we thought about this task of appearance transfer. So what is this task of appearance transfer? So the input are two images. One is denoted as the structure, and the other one is denoted as the appearance. And the goal in appearance transfer is transfer the appearance from the appearance image onto the structure of the structure image. And the challenge in this task is to do that in a semantically meaningful way. So we're not only aimed at transferring stripes on the giraffe. We also want to make sure that the appearance from the head is transferred to the head, and the appearance from the legs is transferred to the legs. So this is the kind of output that we're looking for. And if you think about it, after we saw these cross-image attention maps, what we can do is to basically replace all the self-attention maps of the model when we generate this image of the giraffe with cross-image attention layers, where we're going to take the queries from the giraffe and the keys and values from the zebra. And the idea is to replace the self-attention layers along the entire denoising process in many layers of the model. Okay, and why does it work? So we've seen how these cross-image attention maps look like, but why are we taking the values from the appearance image? So what is going to be, if we take, for example, this red point on the head of the giraffe, what is going to be the output feature here? So as I mentioned before, the output feature is basically a weighted sum of the values, a weighted sum of the values where the weights are determined by the attention map, right? So it's going to be the multiplication between this cross-image attention map and the values of the zebra. So what are we going to get here? We're going to get a weighted average of values on the head of the zebra. And this is exactly what we want to transfer to the head of the giraffe, right? So this is the intuition for why does it work. Okay, so now let's see some results. So on the left here, you can see structure images, on the middle appearance images, and on the right, the output images that we get by replacing self-attention layers with cross-image attention layers. But I guess that you're now quite disappointed because the quality of the images is not really good, and we can see that the appearance transferred in some sense, but it's not the amazing result of the giraffe that I've shown you before. So why do we have these artifacts? So we started to investigate, and apparently what happens is, okay, so what we did was to look first of all on how self-attention map for this image, for the appearance image in this pink point, how the self-attention map look like, and compared it to how the cross-image attention map look like, okay, for the same point. And as you can see, although these attention maps are supposed to represent similar things, they look quite different. In some sense, the cross-image attention map looks much more noisy if we compare it to the self-attention map. So the conclusion that we got to is that there is a domain gap. So previously I told you that the semantic information is shared across different images, but still there are some challenges when we try to combine features from different images that have very, very different appearance. Okay, and of course this happens not only with this example, but also if we take the cars, than if we take a point on the headlight. So the self-attention map looks very clean. But if we look on the cross-image attention map, it looks much noisier. So to solve these artifacts, we basically need to somehow bridge the gap of the domain gap. So we came up with 3 techniques for how to solve that. I'm not going to spend too much time on it because I think the main ideas that are important here are, first of all, to see these semantic correspondences that we can get by looking on the cross-image attention maps, and to understand that there is the domain gap. These specific techniques are not too interesting. But still, let's let me explain them briefly. So first of all, we apply a contrasting operation on the cross-image attention maps. So if this was the example that I showed you previously, if we apply contrast operation, then we get something like that, which already looks much better. And you can also see the improvement in the image that we got. So let me show you again. So this is before applying the contrast operation, and this is after. But you can see that now there is a bit of a misalignment in the colors of the images. So another thing that we can do is to apply a add-in layer to match the statistics of ZT of the appearance image with ZT of the image being generated, and this gives us another nice improvement in the results. The color look much better now, and we don't have the artifacts that we've seen before. And lastly, another trick that quite helped is something that we call appearance guidance. And here, this is very similar to classifier-free guidance, but instead of denoising with and without the text prompt as we do in classifier-free guidance, here we denoise with and without the cross-image attention layer. Okay, and this gives us this improvement, which already looks quite well. So let me summarize how do we perform this appearance transfer. So we have as inputs the appearance image and the structure image. We first of all invert them, invert them to Z capital T, and then we begin a denoising process. Actually, we have 2 branches of denoising. We have a branch for the appearance image and the branch for the image that we're generating. Okay, actually, so for the appearance image, we just denoise it as usual with the pre-trained model. And for the image that we're generating, the image that we want to have the appearance transfer in, we replace along the entire denoising process in different layers of the model. We replace the self-attention layers with cross-image attention layers. So we take the queries from the image being generated and the keys and the values from the appearance image. Okay, and actually, since we also want to have this appearance guidance that I've told you before, we actually have 3 branches. So in the bottom branch, we denoise the structure image, and this allows us to apply the appearance guidance. Okay, so now to the fun parts. Let's see some results. So this method, of course, works not only with giraffes and zebras, but also with you can see here an example of a horse and the kangaroo. And note that here the pose of the horse and the kangaroo is different. And even though the pose is different, we're able to find the semantic correspondences between these 2 animals and transfer the appearance. And it also works with cars. And again, the poses of the cars are different, but we're able to find the semantic correspondences and transfer the appearance. And I think that something that is nice to see, that we're not only, when I say appearance transfer, we're not only transferring the color. For example, we actually find more high-level appearance features, such as, for example, the appearance of the headlight, and we're really transferring it to this red car. Okay, so you can see it in the headlights, and also in the appearance of the windows and the wheels and so on. Another example for a building. So here on the left we have the Eiffel Tower, and on the middle the Sagrada Familia, and we're able to transfer the appearance, and with cakes. And I think this is my favorite example from the paper, because this building on the right look pretty cool. Actually, even after I was in Milan and saw the Duomo in person, it actually, I actually even like this example more. Okay, cool. So what else can we do? So I hope that by now you're convinced that these attention layers allow us to find semantic correspondences between different images, which allow this application of appearance transfer, but which more application this property of the attention layer allow. So another thing that has been shown to be that has been shown to be very powered by these semantic correspondences is a consistent generation. And what exactly do I mean when I say consistent generation? So the consistency can be in different aspects. Okay, so we're going to see two different works that allow for a consistent generation. So in the first work, the goal is to have consistency in terms of the style of the image. Okay, so for example, we want to generate different vehicles, toy train, toy airplane, and so on. And we want to have a common theme for these images. We want it to look like a black and white logo with high contrast. So what happens if we just try to generate this consistency using a prompt? We can just take different prompts like a toy train, black and white logo, high contrast, toy airplane, black and white logo, high contrast, and so on, and just generate it with stable diffusion. But the problem is that we get here, so this is what happens when we try to do that. Here the style is minimal origami style, but as you can see, we don't really have a common theme. All of the images are aligned with the prompt. In all of the images we see this minimal origami style, but the style does not look aligned between the different images. And we're interested in something that looks like that. Images that have a common theme. So the way that they propose to do that in this work is actually very similar to what we've seen in cross-image attention. The high-level idea is to share the features across the different images. Okay, so for example, we're going to generate this toy train with this specific style, and all of the images are going to look are going to use features from the toy train. And this is what's going to allow them to have a consistent style. And basically the idea, if in cross-image attention we replaced the keys and the values with the keys and values of the appearance image, here the idea is to concatenate the keys and the values. Here it's called the reference features are the features of the leftmost image, the image that gives us the reference style. The target features are the features of the generated image. So as you can see, we take the queries from the target features, and for the keys and the values, we concatenate the keys and the keys of the target image with the keys of the reference image. Okay, and we do the same for the values. So this allows for each image to use both of the image, both the features coming from the reference image. So this allows the image to get the style of the reference image. But since we're also using the keys and the values of the image being generated, we're also able to generate the right content. So for example, if our reference image is this firewoman, by taking both the values from the reference image and the image being generated, we're able to have the same style for this gardener, but still to have different features of a gardener. So this is another nice example. And actually, we can also apply this process to real images by, again, by inverting the images. So here you can see different famous landmarks. And actually, my advisor really liked this example. So he actually made the poster out of it and put it in his office. Okay, I will stop for a minute. I see that some people asked about inversion. I'm not going to get into that, but the inversion basically is the process of given a real sum. Let me maybe draw a bit. So usually in diffusion models, wait, let me stop the laser. Okay, so usually in diffusion models, we start from a Gaussian distribution, and we want to denoise a sample from the Gaussian distribution to the real data distribution. And in inversion, we're doing the opposite process. We start from a real image on the data distribution, and our goal is to find the Gaussian noise, such that if we take this Gaussian noise and input it into the diffusion model and start denoising it, we're going to get the image that we started from. And this is a very useful tool, generally speaking, for image editing. Okay, so that was just that you can understand what I mean when I say inversion. Okay, so that was about generating consistent style. But as I said before, consistency of generation can be not only in the style, but also in other aspects. So another recent cool work is called consistory. Here, the goal is to have consistency mostly in the content, mostly in the main subject in the image. So for example, if we have this prompt, a photo of an old man wearing a hat, we want to generate the same man walking in the park, writing numbers on a blackboard, drinking beer in the bar, and so on. And the main application of this task is for a storytelling. That's why it's called a consistory. Okay, so usually if you just take these prompts and input them into the model, you're not going to get the same character. And I'm not going to dive into all the details, but just the high-level concepts here. So first of all, and this is the reason that I wanted to talk about this work. First of all, they share, when they generate this set of consistent images, they share the attention within the object mask across the different images. So you can see this is the figure from their paper. You can see here the SDSA. Basically, it means that they apply this shared attention mechanism across the different images within the mask. Okay, they don't want the entire image to be consistent, but only the main subject in the image. Second, another thing that they do, they actually find explicit correspondences between the different images, between the main subject in the different images. They find these correspondences with a method called the DIFT, which basically which is based on the attention features. And after they have these explicit correspondences, they actually inject features from one image into another. This is this feature injection block here. And another thing that they do, so these two things very encourage the consistency across the different images, but they also don't want that the images will be exactly the same, right? They want in some image the man to drink, and in another way the man to walk. So to encourage diversity, they use some dropout mechanism in a very high level. They don't share the entire features. They do some masking. Okay, so they don't. So for an image being generated, they don't give it access for all the keys and values of the reference image, but only to some of them. So this is the high level idea, and as you saw here, the results that they get are quite impressive. This is also very related to personalization. I'm not sure if you talked about it yet, but this is a bit easier task than personalization because you don't have to be accurate for a specific reference image. You just need to make sure that the set is consistent. Okay. Okay, so until now we mainly talked about semantic correspondences and how are they useful. So now let me show you that these attention features can also be employed for segmentation. So first of all, if we generate an image and we stack the self-attention maps and apply PCA on it, a PCA for 3 channels. So as you can see, again, I said it quite a lot of times, but we get very semantic information, right? We see that although the appearance of the color of the pants is not solid, we get the same color for all of the legs region, which shows that this information is not mainly about the appearance, but about the semantics. So how can we employ that for segmentation? So given an image that we're generating, again, we can stack the self-attention maps in a specific layer and the specific timestamps. So this gives us, if the dimensions of the image are h times w, then this gives us h times w maps, which each of them is h times w, right? So another way to look at it is that for each pixel in the image, we have h times w feature vectors that tells us for this specific pixel what are the pixels that are related to it. Okay, so we have for each of the pixels, we have h times w feature vector. And a very simple operation that we can apply here is clustering, right? For each pixel we have a feature vector, we can just cluster these features. And as you can see, we get quite nice segmentation basically for free, right? The model was not trained for segmentation, and it's a very very simple thing to do to cluster features. One problem with this mechanism is that, as you can see, for example, here we applied k-means. So we need to know somehow in advance how many segments do we want. And as you can see, we get several segments for this cat. So another thing that we can do, again, for free by just using the attention layers, is to label the segments. And how can we label the segments? So if the prompt is a cat wearing sunglasses, so we can take each of the textual tokens, look on the cross attention map. And okay, so for example, this is the cross attention map for the word cat, and this is the cross attention map for the word glasses. And and for each segment, we can find the word that has the highest intersection with this word. Okay, so for example, for this blue segment, we can calculate the intersection of this segment with each of the cross attention maps. And as you can see, we're going to get the highest score for the word cat. And after we label each of the segments, you can see that we get a very nice segmentation, and again for free without any supervision. And why am I talking about segmentation? Basically, it's very useful for many types of image editing tasks. If you want, for example, to blend the background to make it accurate when you're editing the cat, so this segmentation method allows to do that. So let me show some results. So you can see here the segments that we get from the clustering and the labeling that we get from this mechanism. But I'm sure that many of you are now asking themselves, okay, but we have a lot of very powerful segmentation methods, so why is it necessary to use the diffusion model for segmentation? So first of all, I think it's very useful for, as I said before, for different image editing tasks, because in some cases you want to segment the image while it's being generated, and not only at the end where it's fully denoised. But actually there is more advantages for being able to segment generated image. So it turns out that the model really knows what it wants to generate, right? So for example, for this image of the fish, you can see that here there is a fin, and the model, even though it's quite difficult to see it, this fin, the model knows that it wants to generate this upper fin of the fish, and therefore it's able to segment it accurately. And actually, if you take this specific image and try to segment it with SEM, at least the previous version of SEM, and the other state-of-the-art segmentation method, so most of them fail to detect this fin. So this is another nice property that, again, the model knows what it wants to generate, and therefore it's able to get very nice segmentation for generated images. Okay. Another very useful application of attention layers is image editing. It's a whole topic with many work, so I'm not going to talk about all of them, but just to give you maybe a teaser. So first of all, what is the task? So let's say we have this image of a lemon cake, and we want to turn it into a chocolate cake or a beet cake or a pasta cake and so on. And let's assume that this is actually, it's not just an assumption, this is a generated image. So we have the initial noise that was used to generate this image. We have the seed. So a very simple thing to do is to just try to use the same seed, but changing the prompt. So if we try to do that, we do get chocolate cake and beet cake and pasta cake, but they look very different from the lemon cake. It doesn't really look like editing of the image. And in image editing, we want to preserve the original input image. So we want outputs that look more like that. Okay, so we have a chocolate cake and a beet cake, but they're very similar to this lemon cake on the left. So a very common idea that people use, and again, it's a whole topic, and I'm not going to get into all the details, but we've seen before how injection of features along the generation can help for different generative tasks. So here the idea is that if we want, for example, if we have this prompt, a fairy bear watches a bird, and we want to change just the word bear, for example, to a cat, then we're going to inject the attention map of the word bear while we're generating a cat, okay? And this is going to help us to preserve the structure of it, and therefore we're going to have an alignment with the input image. So I think the first work that did it was prompt to prompt. So we can see here very nice examples. There are different types of edits, and each of them is done by a bit different operation on the attention map. But basically, the idea is to preserve attention maps and therefore to preserve the structure of the image. So, for example, here, a photo of a cat riding a bicycle, and we want to change the bicycle into a car. So the idea is to inject the cross attention map of the word bicycle while we're generating an image with this prompt with a car. Okay, so this was just a very short introduction about image editing with a tension layer. And now I want to ask you a question. So previously I showed you how can we transfer appearance from a zebra to a giraffe. But what happens if we try to generate a giraffe and a zebra at the same image? So for example, let's take this prompt, a photo of a giraffe and a zebra in the savannah. And if we input this prompt into SDXL, the first image that I got when I prepared these slides is this one. Okay, so on the one hand, we got another way to do appearance transfer. But on the other hand, of course, it's not what we meant to get, right? We wanted to have a giraffe and a zebra, but we got two animals with the structure of the giraffe. One of them has these stripes of the zebra, and one of them has the appearance of the giraffe. If you look closely, you can see that this part of the legs here look like a giraffe, and the other parts of this animal look like a zebra. So we really got a mix between a giraffe and the zebra. And of course, it happens also when we sample more images. Actually, it's very, very difficult to generate correct giraffe and the zebra at the same image. So here you can see that we got a hybrid between a giraffe and a zebra. And also here we got the neck of the giraffe and the body of the zebra, very strange hybrids. And of course that it happens not only with giraffes and zebras, but also with prompts that may look very simple, right? If you take this prompt, a ginger kitten and a gray puppy in the yard, and try to generate images using SDXL, you get very, very similar artifacts. So here we see that there is a missing puppy. We got two kittens. Here the colors are wrong. Here we got an extra kitten. And here we got a hybrid between a kitten and a puppy. So probably you now wonder why does it happen? But if you think about what we've seen about the semantic correspondences, that was very useful for appearance transfer and for consistency. So maybe it's not that surprising, right? Because if we try to generate a crab and a frog at the same image, so for example, a query on the leg of the crab is semantically similar to the leg of the frog, so it's going to have attention to the leg of the frog, right? So this is actually the attention map that we get. We see that we get attention to the leg of the frog, even though the point is on the crab. So by definition, this crab is going to get values from the frog. So it's going to share features with the frog. And we call this property leakage between the two subjects. Features from the frog are leaking into the crab because they have some semantic correspondence. But this leakage happens not only because of the self-attention layers, but also because cross-attention layers. Okay, so what happens when we try to generate two semantically similar subjects like a kitten and a puppy? So their queries are going to be similar because, as we've seen, queries contain semantic information, so leg is going to attend to a leg, and actually you can even see that here it's a kitten and a puppy. It's a PCA visualization of the features, and you can see that the features of the kitten and a puppy look very similar, their queries. So if the queries are similar and we multiply each of them with the same keys, so their attention vectors are going to be similar by definition, right? Because we're multiplying similar things with the same keys. And if their attention vectors are similar, so again, they're going to share values and we're going to have leakage. Features from the word puppy are going to leak into the kitten and vice versa. And another way I think this is another interesting way to look at it. So let's do the following. So let's generate an image of a kitten and image of the puppy. And let's take from a specific layer towards the end of the denoising process, let's take the queries and project them to 2 dimensions with PCA. Here we generated the images separately. So you can see that the distribution of the queries of the puppy and the queries of the kitten have some overlap, but they're not exactly identical, right? So what happens if we try to generate the kitten and a puppy at the same image? So as we've seen, the queries of the kitten and a puppy are similar, right? So in the output, so as we saw before, since the queries are similar, we're going to have leakage between the kitten and the puppy. And just to make this point more clear, why the queries are similar, we see it on the left, right? Here we generated the images separately, and we see that there is an overlap in the distribution. So that's what we're going to have leakage. So the input of the next layer is going to be even more similar, right? The features of the kitten and the puppy. So we're going to have even more leakage at the next layer. The leakage is going to be accumulated. And we have many attention layers, so we're going to have a lot of leakage by the end of the pass in the model. And in diffusion models, we apply many steps, right? Many denoising steps. So this leakage is accumulated not only across the layers of the model, but also across the different time steps. And indeed, if we do the same experiment, if we try to generate a kitten and a puppy at the same image, and we look and we project the queries to 2 dimensions with PCA, we see that by the end of the denoising process, the queries are completely mixed since we have this leakage, and also you can see that in the image, right? That we got some hybrids between a kitten and a puppy. A common way, so this problem is related to another big topic, which is called misalignment between the text and the image being generated. And a common way to resolve that, wait, sorry, you see my entire screen, right? Not the one with the comments.
Yeah, we are seeing the entire screen.
Okay. I was confused for a minute. Okay. So a common way to resolve that is to optimize ZT along the denoising process. Okay, so along the denoising process, before we denoise ZT into ZT minus 1, we apply the model, we compute some objective. The objective is about the alignment of the text and the image. We backprop through this loss. We compute the gradient with respect to ZT. We get a variation of this ZT, and only after we optimized it, we do the denoising step to get ZT minus 1. Okay, and to make this problem of the alignment a bit easier, it's also possible to input, in addition to the text, to have a spatial layout input. Okay, so in a work called layout guidance, they did this process of optimization. Okay, cool. So it's a nice teaser for the next weeks. So in this work layout guidance, they do this process of optimization, and to define their objective, basically they require that the attention of each of the subject will be concentrated in its corresponding bounding box. But a problem with this approach is that they require the query. So if they want the attention of the kitten to be only within the box of the kitten, and the attention of the puppy to be only within the box of the puppy, basically it means that they require that the queries of the puppy will not attend the queries of the kitten, and vice versa. The queries of the kitten should not attend the word puppy. But as we've seen, the queries of these two subjects, even when we generate them separately, are similar. So what happens when we try to do that is that we do get queries that are much more separated, but since it's not a natural thing, in the sense that even in this reference distribution, we have some overlap, so it pushes them too much far away, so they get into an out of distribution region, and indeed you can see that in the image, right? We got pretty out of distribution image. So in a recent work called the bounded attention, we did some step toward resolving this leakage. We don't have a lot of time, so I'm not going to get into all the details, but just maybe the high level. The idea is to bound the attention so that each subject is not influenced by other subjects in the image. Okay, so the kitten should not, we bound the attention so that the kitten is not influenced by the puppy. We also call this paper Be Yourself. The reason for that is that each subject should be evolved only by looking at itself and not by being influenced by other objects. So I will skip a bit of the details. And indeed, we see that if we use this bounded attention mechanism, we get a distribution which is much more similar to this reference distribution that we have on the left. And also we see that in the image, we got a kitten and a puppy. This is another result. Here you can see a gray kitten, a ginger kitten, and so on. On the left, when we try to generate this prompt using SDXL, we got wrong number of animals and their colors are wrong and so on. And with our method, we were able to get much more accurate result. This is another nice example. But I guess that many of you that are that know the recent state-of-the-art models may ask, okay, what happened? Maybe just the model is not good enough. What happens, for example, in Flux? So one of the first prompts that I tried with Flux was this prompt of the zebra and the giraffe, and indeed you can see that Flux do much better work with this prompt. But it's not very difficult to make it fail. If we make the prompt a bit more complicated, this is the prompt that we've seen before. So there's supposed to be a unicorn, a hedgehog, and a owl. So you can see that in two of the images, we didn't even get the correct number of animals. And here the owl doesn't really look like an owl. And also I think the hedgehog doesn't really look like a hedgehog. Here we got, again, this hybrid between, you see that the hair of the unicorn looks like a hedgehog, but the body looks like a unicorn. So even though better models are better with with some prompts, still the fundamental problem of this leakage in attention layer still holds, and we still look for ways to resolve that. Okay, so let me give some bottom lines for this talk. So I think first of all, then maybe one of the most important points is that attention features contain semantic information, and this information is useful not only within the same image but also across image, and this allows us the appearance transfer application that we saw and the consistent generation. The second point is that attention map provide semantic correspondences basically for free. Okay, so I think that I've shown you some applications, but I think still there is a lot of room to think about more applications which can use this property. Playing with attention features facilitates many image synthesis and manipulation applications. Again, there is a huge line of works that do that, but I still think that there is a lot of room for more applications. And although these attention layers have all these nice properties that we've seen that facilitate image manipulation applications, there is still this fundamental problem of leakage that these attention promote. And I really believe that in some sense, attention layers were not specifically designed for generative models. And maybe we should think about approaches to make these layers more suitable for generative tasks. So that's it. Thanks for your attention.
Yep.
I think we can now, if there are any questions.
Yeah, thank you very much for the great lecture. So yeah, I think this was really great summary of the recent research about like guiding the diffusion, the denoising process by manipulating the attention models. And you have shown lots of the very great examples, like doing some like appearance transfer, style transfer, and also image editing, and also even achieving the segmentation map of the objects as well. So this was really great summary. Thank you.
Thanks.
Yeah, and so let's take some of the questions from the audience. Let me.
Yeah, I see that someone said that in Be Yourself, maybe we get better results because we just have another input. So this is completely correct. This is an assumption that makes the task more easy, and we still. I really hope that in the near future we're going to have a method that does not that prevent this leakage, but does not require these bounding boxes. So this is true.
Yeah, so while we also wait for some more the questions, some of the things that I was also wondering was that so the typical the noise prediction in network of the diffusion models will have some lots of the layers, and each of the layer has basically the attention the module. So I was wondering whether there would be some kind of the more important layers. So in terms of like when you do some manipulation, is it like more important to focus on like some specific layers, or are some specific layers are basically affecting more into some semantic kind of the meanings? And also we can do this kind of manipulations for the some specific the time steps of the denoising process. We can also focus on like early stage or the later stage. So I was wondering whether those kind of the like focusing on some specific time range would also affect the outputs as well.
Yeah. So this is a good question. I think that many of the works that I've presented have a lot of implementation details about doing these injections or assure the attention mechanism in specific layers and specific time steps. Generally speaking, I think that it was shown that at the beginning of the denoising process, more like structural features are determined, the structure of the image that is going to be generated, and at the end of the denoising process, it's more like a fine-grained appearance features maybe. Yeah, so I think it's and also it's true for different layers. At least with the stable diffusion, the layers which have smaller spatial resolution usually control more the semantics and the layout, and the higher resolution layers control mostly more fine level, more fine detail features. So yeah, for example, in cross image attention, we didn't replace all the self-attention layers, but only the layers in the decoder, which have the six or four last layers, those with the resolution of the two highest resolution. Yeah. So and I think that there is a lot of work. Many works explore the differences between different layers and timestamps. One thing that I find a bit annoying is that it's a bit different for different models, right? When we transferred from SD to SDXL, we had to again find the correct layers and time steps. Now that a lot of the models are shifted toward the diffusion transformers, probably we're going to have a different behavior, but yeah.
Actually, that was also the things that I also wanted to ask as kind of the next question. So, because you also have shown like lots of the examples, like not only with the like one single model, but also the stable diffusion XL, like Flux, like those are all different the models, and also they are using different architectures for the noise prediction. So it was also surprising for me that the same kind of the idea, like manipulating the attention of the outputs are actually working with some different architectures of the noise prediction. So I was wondering like whether there will be some kind of the some differences that you have observed in terms of like getting these kind of outputs when you use the different architectures.
Yeah. So I think between SD and the architecture of SD and SDXL are similar enough so that they have similar behavior, and maybe it's not exactly the same layers, but you can find some mapping. I think that with the diffusion transformers, it's a bit unexplored area yet. I think people are still trying to do things. I do believe that the concepts that we used in these works should apply to these models. I do think that there will be we will have to do some changes because the architecture is not exactly the same, but I believe or I hope that some things will be we will be able to generalize them, especially that in diffusion transformer basically all the layers are attention features, so all the properties that we've seen should be even maybe magnified in some sense. But it's true that maybe generally speaking, in this line of works, it's quite a lot of work to when there is a new model. It's very fun because the results are getting much better, but it's also not very easy to adapt the entire ecosystem to a new model.
Yeah. Yeah, and also
Yeah,
there are some questions in the chat.
yeah.
This one is
So in style-aligned image generation, there any specific to apply an add-in only for the query and key while skipping the operation for the values. So I think I actually I don't remember exactly if there is a ablation over that or not. But intuitively, at least, I think that first of all, the reason to apply add-in is to bridge this domain gap that we've seen in cross-image attention, and to bridge this, as we saw in cross-image attention, you need to bridge the domain gap only to find the correspondences. And since the correspondences are determined by the queries, by the multiplication between the queries and the keys, it's not really necessary to also apply the add-in on the values. You actually want to have exactly the same values as in the reference image, but you want to find the correspondences accurately.
also
The
yeah,
next,
About the self and cross attention modules.
Do you think that self and cross attention modules are each adequate for certain types of application? e.g. self-attention or blah, blah, or can we also leverage some interactions between different attention for further enhance? Okay, so this is a great question. I think it really relates to the question that Minuk asked. So in Flux and the Stable Diffusion 3, there is the concept of self-attention and cross-attention layers does not really exist anymore. It's kind of a merge between a cross-attention and the self-attention because it's just about a bunch of text tokens with the image tokens where everything can be attend to everything. So I think it will be very interesting to see what's going on there. What exactly is the question? So yeah, I think maybe the easy answer that I think that it's very interesting to try to investigate the interactions between these different kind of attentions, and Flux I think really gives us the opportunity to do that.
Also, there was a question above there about like how we can measure the the quality of the style transfer. I guess that's
Yeah.
really
So this is a good question for many tasks, I think, in this domain of generative tasks. I think everything that is related to evaluation is pretty difficult and is pretty problematic because you can always find adversarial examples for any metric that you will define. I think that specifically here, the way that we measured, the way that we evaluated was we want to preserve the structure. So we measure the LPIPs between the structure of the output image and the input image. And I think that to measure this appearance similarity, we looked on we basically measured the similarity between different patches of the image. Because what does it mean to have a similar appearance? It basically means that the patches should have a similar distribution. So locally, the images should look similar.
yeah. I think evaluating those things are
And
really
always user study. User study, I think in some sense it's the best way to evaluate things, but on the other hand, when you see a user study in a paper, you don't always 100% believe it because there are many biases and so on. But yeah.
So one more question that I also wanted to ask is like, what is kind of the capability of the diffusion models in terms of the like imagination? Like if we, for example, like if I try to transfer the appearance of the giraffe, not to the other the animals, but for example, like to the human body or to the like car or something, then how much it would work? Like I was wondering like whether it will make some kind of some broken images or still try to make some kind of the realistic, some drop style like human body images.
Yeah. So just to make sure that I understand, you ask whether this method work when the objects are not semantically similar. Do you hear? So in the meantime,
Yeah, I'm hearing.
okay. So the question was whether this appearance transfer method work when the subjects are not semantically similar, right?
Yeah.
Yeah. So of course, that's the method to find these semantic correspondences. We assume that the subjects are semantically similar. So so it's not expected that it's going to work for what you mentioned is, for example, a church and the human body. Although surprisingly, I still not fully understand why it works. We did find examples where it works even between very different objects. So you can see here, for example, the mug and the shirt, or the watch and this iPhone. But generally, of course, it's a limitation of the work that it assumes that the objects are semantically similar to find these correspondences.
Cool. Yeah, so if there's no more question, I'd like to just like wrap up this session with the very last question, because you are also working in the SNAP research, right? So actually, I also wanted to ask in terms of like, what do you think in terms of like how these kind of like some techniques for the generative models are making some real impact in the industry, and also what do you think in terms of like the challenges in terms like applying these techniques to some kind of the real service.
Yeah, okay. So maybe first of all, I will say that I think that the gap between what we see in papers and what we see in actual applications is pretty large. Many of the things are not working well enough to be able to productize them. So so from on the one hand, it's encouraging because it means that many of the things are not solved enough yet. But on the other hand, it means that what we see on papers is not a true picture of the state of the field, I would say. I think that specifically in Snap, we do see that some of the things are getting. I was actually pretty surprised to see how fast things can be shipped sometimes specifically into Snapchat. I also think that there are many engineering tricks that each company has its own tricks, and they're not really maybe in papers you don't really see them, but there are tricks that allow to take these works and make them work better. So yeah, I think that in specifically in Snapchat we do see some things that are shipped, but of course that's the gap between what we see in papers and what we see on the application is pretty huge. I would also say that now on the trip, so I recently bought a new Google Pixel. On the trip that I had now to Milan, I think I was a bit surprised in a positive way of how the taking picture experience is a bit changed. It was a bit changed due to the features that we have now. Of course, again, it's not at the level that we see, for example, in this talk, but still, I feel that the experience of taking picture is being changed, and you start to feel all these nice features.
Yeah, thank you for the great the talks and everything. And actually, we have the like last question. Would it be good to just quickly go over this?
Yeah. So you asked whether appearance transfer can be realized without attention. So generally speaking, I never say that thing cannot be realized in a certain way, because I think that there are many ways that we haven't thought about yet. I think that the specific method that I showed is really built on the observation that attention layers allow us to find semantic correspondences in an implicit way between images. So this work really builds on this observation, which is specific to attention layers, but I'm sure that with other models, there are different ways to do that. And an inspiration that we had for this work, the way the place we started from is a paper, actually not very new one, a paper which is called Swapping Autoencoder. So here they did a similar task with GANs. So I think there is always a way to do things. Yeah, so just to give you some feeling of the results. So I think you can see the inspiration in our results of the churches.
Yeah, this is one of the like relatively like older work using the GAN for this mainly.
Yeah, yeah. So here they do this appearance transfer without any use of attention layers.
Oh, yeah, I think now we can wrap up this session. So yeah, thank you everyone for joining this lecture, and thank you especially Or for giving the great lecture today. Yeah, so let's also catch up in Tokyo in December.
Yeah.
Thank you very much. Thank you.
Bye. Thank you.
Bye.